project, and that's made by EPRO. I see Anto already ready with the video.
Can you hear me?
We can hear you loud and clear.
Okay.
Please start sharing, and we can check that as well. As you might recognize, I'm back again. I did quit Teams and rejoined. So please start sharing. The presentation is coming, and yes, I can see it. So please go ahead, Anto. The floor is yours.
Okay, thank you. Thank you for your time, for taking time. My name is Anto, and I wanted to show EPRO's contribution to this project. What we have done with support of, I must say, very nice TrafoLoss project team members. And before we start, I want you to see some short video. Please watch and listen closely. We have seen that the most important thing for the measurement losses is the very phase error. And this video shows what should not happen if you really want to have low phase error. Don't be surprised by the sound. It should not happen. Okay. Let me tell you, please, what EPRO generally do for living. We mainly produce high voltage test equipments that includes voltage and current transformers and test transformers, toroidal core current transformers, cast resin products, feed-in transformers, and here probably most interesting to mention our automatic transformer test system. Okay. The goal here, especially for EPRO, was to develop a voltage transformer prototype up to 213 kV. Regardless of the high voltage these devices have, the emphasis was on the high accuracy of the devices. As the most important part of overall measurements is the measurement of losses at the transformer, it was planned to take one part from our conventional loss measuring system, and that was the voltage transformer with his digital output. Target accuracy, as you can see, was 15 microvolt per volt and 22 microradian. The target accuracy of the project related to the power, as you can see, is 50 microwatt per VA, and when we show this for different power factor, let's say 0.05 here on the table, then it becomes 1000 microwatt per watt, or 0.1%. Similar for the power factor 0.01, it is 0.5%. So that was the primary project target in sense of accuracy. The first what we have to do were to design and build a voltage transformer up to 100 kV. The reason why we go up to 100 kV instead initially 230 kV is because we think the system can be easily scaled up without any error trade-off. In fact, using higher voltage designs, we can handle the error even much better. So there was one good reason to go further with 100 kV. Generally speaking, the inductive voltage transformers are very stable over time in terms of error and have naturally a low error. In addition to that, we use so-called standard error compensation, and special for this project, the variable error compensation. The standard error compensation is often used, and his job is to set a naturally small error around 0 in value and angle. This kind of compensation is in his value constant over the entire range. That means that you can only slide the error back and forth. Similarly to the standard compensation is the variable compensation. Only difference here is that he can and does change his value over the measuring range. So usually, So usually, at lower range where the natural error is higher, you can have more impact on compensation than at higher range. And this fact, in combination with the standard compensation, can lead to higher accuracy over the entire range and ultimately less uncertainty. And what's maybe important to say is that both compensation, standard and variable compensation, are built entirely with passive elements, so without use of electronics, which certainly has a huge impact on the already existing long-term stability. Up to here we have analog voltage output. To make this digital, we use so-called M-box. This M-box is built in the foundation of the VT. When we talk about the three-phase system, every voltage and current transformer have his own M-box. From there we have our digital wattmeter. Anyway, for this project we were looking more closely at the one voltage channel and try to validate it best as possible. Also the M-boxes have the possibility to compensate some error if it's necessary. You can make tiny corrections on many points over the entire measuring range, both for value or for the angle. Here we come to the validation plan. Since the voltage channel is only one part of the large measurement system, and we really wanted to validate only the voltage channel, the task was then to see how we can validate one part of the system. The plan was to do like showed in the picture 1. We did this by making a special M-box with as less burden as possible, and we assign it to some reference voltage transformer, and that under that I mean the PTB and the EPRO reference, and together with the test object and his M-box created a bridge. The readout was done by the software, which is specially developed for this purpose. We did this with 2 M-boxes because we wanted to see what the phase error is through the software. We had the possibility and planned to check the boxes on absolute error with a precise RMS voltmeter. And we plan to look at the relative error between both M-boxes with use of the mentioned software for readout the values. There we would see if the ratio is equal 1 and phase displacement equals 0. And one more thing we could surely do is to validate the voltage transformer itself with the conventional bridge which PTB use, because the voltage transformer it's the foundation here in terms of the small error. And here we can see the overall equipment, what we tend to use in PTB measurement campaign. It consists of the voltage transformer, the test object, up to 100 kV. This second is the box assigned to him, to the test object. Second box is for reference transformer. This is EPRO's reference transformer. The only difference between these boxes are this one have a lower burden. And the next unit was the data collecting and the supply for the boxes. This is where we prepare the data for the readout software. And finally, the software reader. So where we can read out the values for two boxes and the phase displacement between them. And here we can see how the setup looks like in PTB and EPRO side. On both pictures, we can see setup for the validation of the voltage transformer with his box. So both reference and the test object have digital readout. In the reader software, we can see two things. First, what are the current values of both boxes, and second, the phase displacement between them. The relevant mean value is then calculated from 24 current values. The voltage transformer have 85 kV rated and 50 kV tapped down to 110 volt with 50 Hertz. The measuring points were from 120% to 20%, down to 20%. And last but not least, I want you to show some facts about the complete EPRO measurement loss measurement system. On the graph, you can see one part of the calibration certificate from PTB from 2014. One part is because here I show only the results from lowest power factor we could calibrate at PTB, and that's the 0.05. By higher power factor, it's the results are naturally better. Anyway, this calibration is related to our digital wattmeter with standard voltage and current transformer. The ranges here were from for the voltage channel from 5% to 120%, and for current 1% to 200%. And to cover a wide range of power measurements, all voltages were measured with all currents. In sum, it was 60 combinations, voltage and currents. For example, here on first combination in graph is 25 volts and 0.5 amps. And at the end, the results show that the maximum error is below 300 ppm for power measurement at power factor 0.05. The relative uncertainty from the PTB was, depending on the range, 10 ppm up to 50 ppm. And since then, from first calibration at PTB in year 2014, we offer the customers fully calibrated system, while EPRO is doing the 17025 calibration on the VTs and CTs, and the measuring boxes calibration on PTB primary power standard in Braunschweig. As you could see in our prospect, we tend to round our accuracy to 1000 ppm or 0.1% for power measurement by power factor of 0.05, although the accuracy is better than that. The reason here is simply to provide a better guarantee in more and more important loss measurement. By the way, at the very well-known 0.01 power factor, we only can estimate accuracy on the basis of the angle error we got verified from the PTB. We state in our accuracy table that it is 0.5% from the measuring value at 0.01 power factor and 60 Hz. Thank you for your time. Thank you for listening. If you have any questions, please don't hesitate to ask.
Yeah, thank you, Otto, for the nice questions and the good overview of the work you've done. And I realized that since the start of our meeting, several attendants joined us. We started with a good afternoon and a good evening for our Far East colleagues, but we should have also started with a very good morning for our attendants from the Americas. I think we are now really covering the whole world almost. For those that joined later, in a few words, the TrafoLoss project in the first point focused on improving the voltage channels of industrial systems. That was found a weakness, and there was a need for developing better voltage channels. And the first presentation on that was from VTT, Jari Hellstrom, on the voltage channel that VTT developed. And this is the second presentation in that series from Anto from EPRO on the second voltage channel that was developed, once again with the aim to make better voltage channels available for industrial loss measurement systems. So with that background for the colleagues that joined later, I indeed would like to encourage, we still have time for a few questions. Any questions to Anto? Like maybe one other comment, like you said, and also Jari said, one key aspect of the project is a comparison of all different voltage channels that are developed in the project by PTB. And well, both you and Jari were referring to your equipment being sent to the PTB, and we hope to share the results with the present attendants at a later time when all results are available. I'll come to that at the very end of this workshop. Any questions to Anto on his presentation? Raise hands. I see no raised hands. So then again, thank you, Anto, very much for the clear presentation.
Yeah, thank you. And I like to thank you and